let's apply a little bit about what we learned into calculating the area of a curve between 2 points above the x-axis and below the curve. So the area of the shaded region here. So this is akin to what we did in the first part of this lecture, which secretly was really, I think, problem number 28 with n equal 4 as opposed to n equal 8. I couldn't imagine, the tedium of dividing this up into 8 intervals and doing it all by hand, so I chose to do it with 4. But let's see about calculating this area. Now, I've got a nice formula up here that I have to fill in and understand. First of all, I'm going to try and figure out the height of one of these rectangles. Now, for convenience, not that you have to do it this way, but it is kind of convenient, we're going to assume that we're using the left-hand endpoint of our rectangle, of these subintervals. Let's start by finding the area of one rectangle. And we're going to try and simplify this expression. So there's a few things that go into that. That's this expression, f of c sub I times delta x sub I. I guess one thing that I'll do for ourselves, kind of a simplifying assumption for us, is we're going to assume that the partition we choose is evenly spaced. So it doesn't matter if you're working with one interval or the next. Here you can see the partition is spaced kind of erratically. Same thing here. This is an evenly spaced partition, a so-called regular partition. So we're going to assume that we have a regular partition. So you can replace the delta x sub I with just a delta x that we have over here. So that's going to be the width of our expressions. So let's calculate delta x. Delta x is going to be b minus a over c, or b minus a over n. Here's your a and here's your b. That's the width of, well, maybe I should write it down here. A equals 0, b equals 3. But it's from this interval. So 3 minus 0 over n, that's going to be delta x. I next need to find the height of each of these rectangles, and it's going to come from evaluating the left-hand endpoint of all these subintervals. So I'm going to need something before I get to finding the height. Where I'm going to find the height. What's the coordinates of this expression here? The way to do that is to start with the left-hand endpoint and add delta x, delta x, delta x until you get to whatever particular interval you're working with. So we'll call it c sub I is going to be a, which is 0, plus delta x, 3 over n, times I. For convenience, I'm going to write it as 3i over n. So I've got the width here. I'm ready to find the height. I'm going to evaluate the height at this point. F of c sub I is going to be f of 3i over n. Plug that into this expression here. F of x is y, or x squared plus 1. So it's going to be 3i over n quantity squared plus 1. I don't really need those extra brackets there. I'm not sure why I put them. It's all right. They're harmless. But now the product of these two. This is your width. This is the height. The product of those two gives us the area of one rectangle. Actually, you know what? This is your width right there. So the area of one rectangle is going to be like this. Area of one rectangle is going to be 3i over n squared plus 1 times 3i over n. No, not I. I don't want that I there. Sorry. It should just be 3 over n. That's better. So that's the area of one of those rectangles. We need the area, we need to add up the area of all those rectangles. So what's nice here is that we can do that. We can do that with a summation. We're going to create this sum from I equals 1 to n. Then we're going to let the number of rectangles go to infinity so that you actually get, in the limit, the true area underneath this curve. So it's going to be the sum from I equals 1 to n. And let's start cleaning this up a little bit. That's going to be 9i squared over n squared plus 1 times 3 over n. And I want the limit as n approaches infinity. So this is the area of all our rectangles added up. And I'm going to let the width of those rectangles get really, really small. So hopefully my error is going to vanish. And I'll get the exact area underneath this curve. Okay. Let's play around with this a little bit. I can distribute the 3 over n. And that becomes the limit as n approaches infinity of the sum from I equals 1 to n of 27i squared over n cubed plus 3 over n. Let's keep going. This summation is taken from I equal 1 to n. So the things that don't involve the I can take out. In fact, I can distribute this a little bit, make this a little easier to work with. That's the limit as n approaches infinity of, let's see, 27 over n cubed times the sum from I equals 1 to n of I squared plus, and I'm not going to do likewise here, but it's not a big deal, I equals 1 to n of 3 over n. So I'm just playing around with my summations based on their properties. What's helpful at this point is to realize that we can replace these summations with some expressions. Both these summations are going to simplify. So what's that going to give me? Well, limit as n approaches infinity of 27 over n cubed. And now here, that's a summation that I gave you earlier. That summation was n times n plus 1 times 2n plus 1 over 6. Yay, so I got rid of that. At least now it's looking a little bit more doable. How about this one? Notice something about the second summation here. Does it depend on I? No. Earlier we did the summation from 1 to 30 of negative 18, right? And all we did was we just multiplied. So that's what we're going to do here. We're going to take, since this is a constant, it doesn't depend on I, it's going to be n times 3 over n. Now here's a good place you can double check yourself. I sometimes feel it's like not really in the spirit of things, etc., but being more practical, it is in the spirit of things. These exponents, you have an n cubed here. If I multiplied this out, what power of n would I have in the numerator? What degree polynomial? Cubed. I'd have an n cubed. They better match. If they don't match, Alex, then there's problems. So, do they match here? Sure. 1 and 1? Yes. Over here? 3 and 3. So they match. So we're in good shape. Now let's do some simplification. We're almost done with this one. First of all, the ends here cancel out pretty nicely. Secondly, one of these will cancel out, so I'm left with an n squared here. So, looking better. I'm going to rewrite this as the limit as n approaches infinity of, well, we'll write it as 27 over 6. And then when I distribute this, it's going to be 2n squared plus 3n plus 1 over n squared plus 3. So all I did was I foiled this out a little bit. I moved the 6 here so that I can cancel with the 27. Let's see what we get here. First of all, the 27 over 6 reduces to what? 9 halves? 9 halves. What's the limit as n approaches infinity of that rational expression?
2.
So 9 halves times 2 plus 3 equals 12. Okay. Wow. Ooh, ah. Look at that, it all vanished. We got a look. See, we got a nice round number. How cool is that? See, I always give you problems that work out easy, don't I? Nice. All right, little tongue-in-cheek on that one. Ray's not smiling. All right. These are lengthy problems. That's why I only put like 5 or 6 of them on an exam. But I'm kidding. That would be murder for me to grade, just like it'd be for you to take. So no. 1. Expect 1 like this. Exactly 1. All right. Looking back here, we'll do 1 or 2 more like this. Looking back, is there some place that you'd like me to say, well, what was going on here? Or you just kind of want to do another one and just get a little more practice? That's the area of the whole thing. So, in fact, you know what? I think I can edit that little decimals thing that I have. We can kind of look at it there. So here we go. Left Riemann sum. So let's just change this to, let's see, what did we have? We had x squared plus 1. X squared plus 1. And I want to change a couple other things here. So that, and I want to go from 0 to 3. Yeah, come on. Sit. Yeah, we'll just cheat here. 3. Sit, stay. Good boy. All right. And let's one last thing here. Y-axis. Let's make that say 10 or 11. Okay. All right. So let's keep an eye on this as we increase the number of rectangles. So our first estimate is a 3. But as we increase the number of rectangles, should we jump to the happy ending?
Yes.
11.93. Yeah, I think it's looking pretty convincing. That summation that we just calculated. We took this to the extreme. This is only with 200 rectangles. We did an infinite number of rectangles. We got 12. They're still stuck at 11.93. So it's pretty close. But we did a lot better. Okay. Let's look back here. Just 12 is the exact answer. Yes. Yeah. Let's try a different one then. Let's see. Problem number 48. Okay, so problem 48, f of x this time is 3x squared plus 1. Here we're dealing with the interval 0 to 2, so that's your A and that's your B. We'll start by calculating the width of each of our subintervals. So the width is our delta x, and that's going to be b minus a over n. It's just convenient when you have an interval that starts at 0. We won't always be so lucky. 2 minus 0 over n. That gives us the width of each of our rectangles is going to be 2 divided by n. Now that's assuming that we have a regular partition. That is, they're all evenly spaced. And that's fine. We're going to make that assumption. The value of x, where we're going to calculate the height, is given to us by this. C sub I is a sub 0 plus delta x times I. That is, if you're in the first interval, then you need to move a width of delta x over from where you started from. In this case, it's going to be 0 plus 2 over n times I. Basically 2 over n, or 2i over n. No, that's where you're going to find the height. You need to put that expression into f of x to actually get the height. Because the height will be your y coordinate. So the height is going to be f of c sub I. So this is going to be f of 2i over n. 3 times 2i over n plus 1. It's going to get squared. So it's going to be what? 4, 12 I squared over n squared plus 1. So that's the height of one rectangle. Let's find the area of one rectangle, and we'll clean it all up a little bit. It shouldn't be too hard. So the area of one rectangle. So the area is going to be the width times the height, or the height times the width. Let me do it that way. So height times the width, which is going to be 12i squared over n squared plus 1 times 2 over n. So that's the area of one of those rectangles. But I don't want the area of just one of those rectangles. I want the area of all those rectangles. Let me distribute this. That's going to be 24i squared over n cubed plus 2 over n. So that's the expression that I wanted. Area of one rectangle. Well, we don't want the area of just one rectangle. We need to add up the area of all those rectangles. So that's where we're going to do the summation. So it's going to be the sum from I equals 1 to n of 24i squared over n cubed plus 2 over n, like that. And it's not enough that we just add up the area of all these rectangles. Because if you have a finite number of rectangles, then at best you're going to get an approximation to the area. This approximation becomes exact. It actually becomes the area when we do what to n? Perfect, thank you. Take the limit as n goes to infinity. Now let's work on calculating this sum first before we worry about the limits. So as far as working with the sum is concerned, that's going to be the limit as n approaches infinity of, let's see, we'll write it as 24 over n cubed times the sum from I equals 1 to n of I cubed plus the sum from I equals 1 to n of 2 over n. So I'm just kind of playing around with the summation here. And the nice thing is that I can replace some of this with some formulas. I can keep on simplifying these expressions. I squared. Thank you. So let's work with these formulas here. It's going to be the limit as n approaches infinity of 24 over n cubed. And now I need to throw in the formula for the summation of the first squared, or first n squared integers. So it's going to be n times n plus 1 times 2n plus 1 over 6 plus n times 2 over n. We're starting to make some headway here. Starting to see the light at the end of the tunnel. Unfortunately, it's not a train. Fortunately, it's not a train. Okay, so there's some simplification we can do here. 6 and 24. Let's simplify those. So that's going to be a 4 out in front, and we can get rid of one of the n's here. So that'll become a 2. Get rid of that. And then likewise over here, the n's will just cancel all together. So let's see what we have next. Limit as n approaches infinity of, that's going to be 4. And we distributed this before. That's going to be 2n squared plus 3n plus 1 over n squared plus 2. One thing I would appreciate, even though it gets cumbersome, I know it, but these things are only equal as long as you're carrying around the limit, especially in this last step here. In this last step, I'm going to get 4 times what? 4 times 2 plus 2, which is 10. So 10, that'd be in square units. All right, are those looking better? I mean, I know the first one was probably pretty rough. Second one, yeah. Donnie, something I can help with? Yeah, so as you're approaching infinity, what happens is that these two things have the same degree, so the limit is just the ratio of the leading coefficients. 2 over 1 is 2. Yeah. Which 3 are you talking about? Talking about the exponent here? Oh, the 3? Yeah, this one just gets drowned out. All right, because n squared is so big compared to n, when the values of n get pretty large, it just doesn't matter. So the limit of this, even though we have a 3n, if you could have a 3 million n here, the limit would still be governed by the ratio of the leading coefficients here. Yeah, so that part just doesn't really come into play. So appreciate the question. Anything else on 48 that I can help with? Okay. Let's try problem number 46. So y equals 3x minus 2. I'll also call that f of x. This time we're dealing with the interval 2 to 5. Yep. Well, yeah, we're going to use this function. This is going to help us calculate the width of our intervals. So delta x is going to be 5 minus 2 over n, which is going to be 3 over n. C sub I, though, it's going to be a little bit more cumbersome. Remember, it's going to be a plus delta x times I. A is no longer 0, which is a little bit annoying. It's going to be a 2. 2 plus 3 over n times I. And I need to plug that into my expression for f. So this is my width. And here comes the height. F of c sub I is going to be 3 times 2 plus 3 over n times I minus 2. So let's clean that up a little bit. That's going to be 6 plus 9i over n minus 2. And finally, 4 plus 9i over n. And that's my height. Let's use that now to find the area of one rectangle. So we're just going to kind of squeeze it down and find the area of one rectangle and see what we get. Area of one rectangle. So it's going to be the height times the width. So we have expressions for both of these. It's going to be 4 plus 9i over n times the width, which is 3 over n. 12 over n plus 27i over n squared. That's the area of one rectangle. We need to find the area of all such rectangles. So that's going to be the sum from I equals 1 to n of 12 over n plus 27i over n squared. And in order for this to actually be the area, I need to take the limit as n approaches infinity. That is, let the number of rectangles increase until their width is infinitely thin and the error terms go to 0. As before, we're going to kind of play around with this limit and break it up. In fact, tell me what you think. Do you want to try and handle it from here? All right, give it a shot from here. See if you can't finish this up. First one with the right answer will get Mimi to carry around your books for the rest of the semester. While you're working on that, I'll see if I can't change up our little demonstration to see how it compares. Bless you. How you guys doing on these? Okay. So the first thing to do is to replace these with some formulas. This is a constant. It does not depend on our index of summation here. So it's just going to be n times the constant. So I'll have an n here times 12 over n. This is a constant times the formula for the sum of the first n integers. What's that formula? Good. N times n plus 1 over 2. Now, if you remember a little while ago, what I suggested was that you always make sure that these exponents match. If they don't, stop. This is a really big point problem on the exam. You don't want to be stuck here with a cube here and a second power here, or a second power and a fourth power, etc. These should match, and they do. So let's finish this up. We get some cancellation here. That's just going to be a 12 plus 27 over 2, n squared plus n over n squared. What's that limit going to be? Oh, I canceled those. Oh, I guess I could have canceled one of the n's. Yeah, I should have, maybe. But it doesn't matter because you got an n squared and an n, right? So this limit here is going to be a 1. So overall, I'll get 12 plus 27 over 2, which is going to be 25.5. Or you could write it as 51 over 2. Doesn't matter. Still get the same thing. Let's look at it with our little app, our Desmos kind of app. So I've replaced our function here, starting out at n equal 1, etc. And it takes a while. So at n equals 60, 25.275, n equals 150, you're still at 25.41. It takes a while. Let's just go to the happy ending. So all the way up at n equals 500. Boy, at n equals 500, still not quite there, 25.473. I mean, suggestive a little bit, but it's not completely convincing that the true limit is 25 and a half. Sure. Sure. Let's look back at that and cancel out those n's. So let me rewrite this then. So we had the limit as, so jumping down from here then with the cancellation of the n's, it'd be the limit as n approaches infinity of 12, right? Because those still cancel, 12. And if I canceled one of these ends, I'd be left with 27 over 2 times n plus 1 over n. And again, these two things, they match in terms of their degree. So the limit there is the limit of the ratio of the leading coefficients. So it's still a 1. So it still works out to be the same. All right, not a problem. Glad to oblige. 51 over 2. Great. All right, let me give you some homework. For homework, try 1 through 33, 37, 39, and 45 through 49. These are ones like that we finished up with, the area problems. And I'm not going to give you anything really obscene in terms of an area problem to deal with. You're not going to have to deal with sine or cosine or tangent or anything like that. It's just going to be very, very simple polynomials. So have a great weekend. See ya!